Hi, and welcome back to another LeetCode problem. We're looking at LeetCode 270, closest binary search tree value. It's an easy problem. I have tried this before, but quite some time ago. So I'm going to attempt to solve this one again. I like tree problems. So yeah, let's see what we got here. Given the root of a binary search tree and a target value, return the value in the binary search tree that is closest to the target. If there are multiple answers, print the smallest one. Wait. And what do you mean by closest to the target? Okay, we have to find that out. The number of nodes in the tree is in the range from 1 to some high number. So we have at least one node. The values are also all positive. And the target is a number that can be larger. Well, can be as large or much smaller than the nodes in the value. Okay, let's look at an example. So we have a tree here and the target is 3.7. So what is the closest value to 3.7? Well, this is a binary search tree, right? So we go to 4. Now we check whether our target is smaller or larger. And then we decide in which direction to go. And I guess we go down that path trying to find that value, which we might not find at all. And along that path, we have to pick the one that is the closest to target. That's what I would think. Okay, here's another example. Root is 1, target is blah, blah, blah. There's only one node. That has to be the closest one. Okay, cool. All right, so I think we can implement that in O of h time, where h is the height of the binary search tree. And the height is, of course, bounded by the total number of nodes. If we have like a tree that is degenerated to a linked list, then that's the worst case, where the height is equal to the number of nodes in the tree. And we're not, we could implement it in two ways. We could implement it as a recursive solution or as an iterative one. If we do it as a recursive one, we will have to use stack space, which is O of h or O of n in the worst case. And if we have an iterative one, we really only need to remember the smallest node or the closest node value and the current node. So that would be actually constant space. I suggest we implement both just for the fun of it. So let's go for the recursive one first. O of n time and O of h space. N and h, and when you talk about n and h with trees, it's obvious that you're talking about the number of nodes and the height of the tree. So I'm not going to comment with that. Comment that even further in writing. Okay, cool. So we're going to have a little helper method, node, target, and yeah, that's what we do. And we only need to return an integer value. So I guess we just return the node value that we want to find. Cool. So if not node, well, then there's nothing to do. But we are guaranteed to receive at least one node, right? Number of nodes and trees at least one. So okay. Okay, cool. So we will return DFS helper on the root node, and we'll specify our target. Now, when we enter this method for the first time, we know that root is not empty. Now we can determine on our way up on the tree what the closest node is, and we will just return it every time. So let's first deal with going into the left and the right subtree. So we have to check it here. If node.left, if node.right, right? Well, we have a result here. What is the closest node? Well, it's always going to be the current node on our way down, at least, right? And closest value. So if we go into the recursive call, we have closest value left on the left side equals DSS helper node.left.target. Now we also get the closest value on the right side. Or what is this doing? Closest node on the right side. Or closest value. Node dot right. So we get those two. And yes, I'm just going to initialize those values with also the current node value, just so that we don't have to do any other if else blah 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 and set them independently. So we just set them all to, we just set them like so, to the current node value by default. So now we have to check which of these three values, the closest value to the right, the closest value to the left, or the current node value, which one is the closest? Just trying to come up with a better version of this. So what if we like use an array of this? So we just put that value in 3 times, and then we just say res at position 1 is that, and then res at position 2 is that. That would work, right? So now we just have to iterate over all of these 3. So for val in res, if abs val minus target is smaller than abs val target min val or closest val target. In that case, we need to update our closest val to the target equals val. So that's the node value that is the closest for target, but we also need to initialize that to node.val. And I guess, yeah, that's pretty much what we need to do. And we actually only need to have 2 of these entries. We use them as res1 and res2. Yes, that's what we'll do. Okay, cool. And I think that would be everything. I think that is the whole thing, the whole deal. So let's walk through an example. So we're running into, let's use this one. We're running into, oh, this, by the way, is not necessary because we're running into both subtrees, left and right, you know, and we haven't really exploited the fact that this is a binary search tree. So actually, we always, even time is going to be, well, log n time, no, h time over n time, over h time and space, because we only need to explore all the nodes that are on this path that when we're trying to find that node. So if node is left, well, the first check we need to do is the binary search check, in which branch are we going to get. If node.val is equal to target, return target, we're done. If node.val is larger than target, well, then we should go into the right subtree. If node val is smaller than target, if it's smaller than target, we need to go in the right. If it's larger than target, we need to go in the left subtree. If that is the case, and the left node exists, then we do that. And similarly, if the value is smaller than target and the right node exists, then we're going to go into the right node. Right, so, and we probably don't need to check that case. And we also don't need an array anymore. because we only need one result, because we're only going down one path. Okay, that simplifies things. I should have seen that earlier. And now we just check if the absolute difference between our node value and the res value, right? Then we return node.val. Otherwise, we return the result value. So that one or that one. That's pretty much it. So let's put that to the test. Node.val minus target. Unsupported operator for type none, none type, and float. How can it be none? How is that even possible? Because we're not returning result, right? So we do res and like that. Cool. So that passes our tests. If we submit that, that should also work. But we're getting the wrong answer. Target was, and we're returning 5, but we expected 4. How is that possible? So that, let's look at that tree. We have a tree with root 4. It has a child 2. And it has a child 5. And then here we have a child 3 and that. Okay. So we go here. We're looking for 4.5. That means we go right. And which one is now closer? 4 or 4.5? Oh, there was a constraint on if you have multiple, return the smallest, right? So we actually have another case that we need to consider. And that is if the difference is the same, then we return the minimum of node.val and result. That's what we'll do. Right? If it's the same. Okay, so let's try to run this again. That works. Let's see if that works now. Or if we run into an issue because we don't do an else if. So that works. Okay. Cool. So we spotted that we can reduce the time to O of H time and space by exploiting the fact that we are using a binary search tree. Now we still use O of H space here. So the second approach would change that so that we have O of H time and we use time and O of 1 space using an iterative approach. So let's implement that. So, well, for the iterative approach, we just need to have a loop while true. And we can just use the root node for our operations. But to make it clear, I'm just going to rename it like this. So, well, we basically have to apply the same logic as we did before, right? So in the beginning, our result is just going to be node.val. That's the first thing. And at the end, we're going to just return the result, which we are going to update inside our while loop. While true. Okay, so we have to test into which subtree we go. So maybe we should add that first. So if node, well, it's basically the same thing that we have here. So we can just copy that. And what we'll do is node equals node.left. So that's what we'll do. And we do node equals node.right. We're actually updating the node in the iteration. Otherwise, we just could turn node.val. That's what we do. So if smaller, we go right. If it's larger, we go left. Right, left, right. And if it's the same, we're done. We can just return the node value. That's all we need to do. Cool. So, well, now we need to add the part where we compare. Well, if we can find a better result. So at every step, let me see. If node dot, I see. Well, we didn't really finish it entirely. Else if node.wall equals target, we need to have that. And otherwise, we know that we're done. We don't have anything else to do because either node.left is none and we wanted to go left, or node right is none and we wanted to go right. But none of those things happen. So that means we're going to break out of the loop. And yeah. Well, we could just say while node, I guess. And then what we'll do here is we just set node to none. We'll do that. That's maybe too complicated. Why would we want to do that? Since it's guaranteed that our root node is not none. Cool. So that is that. Now, after taking a step, we have to compare. So if we take a step left or right, in the next iteration, we have to compare to see how close we are now to our node. So we could go maybe diff. We just call this diff. This is ABS of our node minus node val minus target, right? And the current diff is basically our result minus target. And then what we do is if current, well, if diff is equal to current, that's the logic we had below, or else if diff is smaller than current, then we just say the result equals node.val, which is the current, well, which is the, this is a the wrong formulation. So the previous smallest, if the current distance to target is the same as the previous distance to target, we have to pick the node that has the lower value. So if res smaller than node dot value, nothing changes. But if it's larger, in that case, we have to update our res to node.val. That's all we need to do in this case. However, if the current one is smaller than the previous or the closest one, well, we just update our previous value. So previous val is maybe what a closest val, closest. Actually, so it's the result, right? So we just put that to result instead of res. Right. Yes, and I think that should be everything. Let's run this code. Oh, there's an error. It should be result, not res. Cool. So it passes the test cases. That's a good sign. And we now submit it to see if it actually passes all of the other cases. And it does. So yeah. So that's an example of how we shaved O of H time away from a problem by turning it from recursive to iterative. And yeah, I hope you've enjoyed that. Try to implement both versions. try to explain the trade-offs, right? The recursive one clearly is much easier to implement, much easier to do, because binary search, search in a binary tree is very easy to implement and very intuitive. You see, you only have like a couple lines of code, but the iterative one, well, it's a little bit more convoluted. You need to pay a little bit more attention to detail, etc., etc. So that is, I guess, the trade-off. The implementation of this one is easier, but it requires O of H space, and the iterative one requires only O of 1 space. And that concludes that video.